In this video, we'll begin talking about Chapter 19. In Chapter 19, we will look at the reactions that happen on aromatic rings. On our aromatic rings, we have to have very specific conditions, and in particular, we're going to focus some of our efforts talking about how we make the electrophiles for these reactions. So our first reaction is going to be the electrophilic aromatic substitution, and how we make these electrophiles is going to be able to make them very electrophilic so that this reaction can happen. So if you recall from the previous chapter, aromatic molecules are very, very stable, and so you need to do something to enhance that. So for our chapter question, one of the things that I will ask you to do is look at ways in which you can make benzene into one of the compounds in Agent Orange. Agent Orange was a group of molecules that was used in Agent Orange in the Vietnam War to clear the brush. It's a herbicide, and allows the U.S. military to be able to know if the Vietnamese were coming towards them or hiding in the jungle, because they would kill all the bush. But the problem is it's still in the soil today, and there's a lot of people now that have cancer from the Agent Orange. And so the two compounds that are the main compounds that are in Agent Orange are these two. And so at the end of the chapter, knowing what we have learned, you should be able to synthesize one of those two, either 2,4-D or 2,4,5-T. So you need to be able to figure out what is the order of reagents and how can we be able to do this, making one of these two compounds. So first, let's start with what electrophilic aromatic substitution is. Electrophilic aromatic substitution is a way that we can add onto aromatic rings that are not very electron poor. So I'll talk about aromatic rings that are extremely electron poor. Now, I'm not saying that these aromatic rings might not be slightly electron poor, but it can't be extremely. And we'll get to that, and we'll talk about what that reaction is later on. But the typical reaction of electrophilic aromatic substitution we're going to draw as a generic reaction. So you take your aromatic molecule, and in this case we're going to use benzene as our example. So this is not the only aromatic molecule we can use. We have to have a very strong electrophile, and we take that very strong electrophile and use the aromatic molecule as our nucleophile. We attack the electrophile, and what you'll notice is we're going to break this double bond in this case, putting our electrophile on the molecule. So it means there's a hydrogen still here. It's understood, you don't have to draw it in, but I'm going to draw it in to explain what's going on. And that would leave this carbon with a plus charge. It still has its hydrogen on there, but the hydrogens, like we said, are typically not drawn in. So there's going to be some sort of base in this reaction, and it will deprotonate that hydrogen where the electrophile is, and this would be our product. So let's talk about why this is and why this works. So at this point, this base is going to deprotonate, and you're going to essentially do first an addition of the electrophile, then an elimination. And that's because this molecule now becomes non-aromatic. And we learned that non-aromatic is less stable than aromatic. And because it's less stable than aromatic, it doesn't want to be that way. And so one way to reattain aromaticity, or to make this molecule become aromatic again, you're going to deprotonate. So in these reactions, we're going to end up with this intermediate, and it's this intermediate that we'll look at under other conditions. This intermediate is one of the things that we'll look at when we have other things on the ring already, and evaluate how those substituents might affect this reaction. This particular intermediate, you'll notice in your textbook, has a name, and we'll get back to that in a little bit. So what we're going to focus on outside of that is how we make the electrophiles to do all of these reactions. And we are going to make the electrophile to make the halogen, the nitro group to do nitration. We'll talk about the sulfonation. This one is more important because, very important, because we can use this as a blocking group or a protecting group on the ring. We'll talk about how we can do a hydroxylation, and when I show you that one, that's not in the textbook, so you definitely want to write that down, because this is one that you're not going to find within the electrophilic aromatic substitution. You have to do something else to get the phenol. And then we have the alkylation, which adds alkyl groups, and then we have acylation to add acyl groups. Now there are other reactions, some of which we've already learned. So if you go back to some of the presentations, you learned how to make aldehydes, and I gave you the way how to make carboxylic acids onto phenols. So you want to revisit these from the PowerPoints from your peers, and I'll revisit this particular reaction. So our first method that we're going to do is how we make the halogens. How do we make a halogen become positive? We know that from general chemistry that it's not easy to make halogens positive. They don't like to lose electrons. They're very electronegative, so you have to do something very specific. Now your textbook has a slightly different way of drawing it, but the way that I want you to draw it on your tests and so on, please make sure you kind of follow this, but you can use the other way, for instance, on Wiley, etc. So we need to make this become halogen that has the plus charge on it, and I'm going to use a Lewis acid. And with that Lewis acid, we're going to be able to do this process. And so in this process, you will take that Lewis acid plus the halogen itself. Now, the types of Lewis acids you can use varies. So for instance, with chlorination, we'll oftentimes use aluminum chloride or boron trichloride. For bromine, we'll oftentimes use very similar things: aluminum bromide, boron bromide, etc. For the purpose of class, it doesn't matter which of these that you use. The point is that they have to be the Lewis acid that's equivalent to the halogen. We'll talk about iodide and chlorine separately, iodine and fluorine separately. The mechanism for this, and I'm going to draw one as an example. You take your Lewis acid and you take your halogen, and remember that the aluminum chloride, being your Lewis acid, has an empty p orbital, and this empty p orbital can accept electrons from the lone pairs on the chlorine. Same thing with bromine, and we get this intermediate. That makes this very positive, and it's not terribly stable to have your structure with the aluminum and the chlorine next to each other with these charges. And so what happens next is that this can get the electrons going that way. This is still going to be negative. This becomes AlCl4, which is a base. Note in the mechanism when I drew before, you needed a base, and you get Cl+. Now this is very unstable, so it will react very fast in your mechanism. Now your textbook doesn't, I think, draw the mechanism out completely. It kind of shortcut it. This is the full mechanism, so please draw out the full mechanism. On your tests, this is what I'm expecting of you. So if you take your aromatic ring, again, we're just going to use benzene as our example. You have Cl+, it's very unstable, so immediately, as soon as it forms, this is going to, the benzene is going to attack the halide cation, which is highly unstable. You get your very unstable intermediate, and your base will come in, and this line goes from the bond, that's where the electrons are in this molecule, so from the chlorine to the hydrogen, and then that will break this bond and you'll get this. You'll end up with chlorobenzene plus HCl, because that chlorine comes off and takes the hydrogen with it. So I'm going to use a slightly different color. So this chlorine came from here. Doesn't matter which of the chlorines you started doing this with. And you'll get your AlCl3 back. So what does that mean for AlCl3? That is a catalyst. So this is a catalyzed reaction. So you only need to use a little bit of the catalyst, and the same thing happens when you do bromine, the same exact mechanism. So instead of chlorine, you would use aluminum tribromide with bromine, and you'll get the exact same mechanism. So what are some examples of these reactions? So we can take benzene and we can use the Lewis acid. So another example of the Lewis acid is iron trichloride. So you can use iron trichloride, aluminum trichloride, boron trichloride, as long as it's one of those Lewis acids. An application of these reactions is that you can make diazepam, which is a molecule that is used for things like anxiety, muscle spasms, withdrawal. It's basically something that can have a calming effect, and its name on the market, if you buy it in the name brand, is Valium. So if you've ever heard of Valium, that's what it is, and it's used, it's made actually. Now, fluorine is way too reactive to do these kinds of mechanisms, so most people don't do them. We'll see later on there's an example where you do use this. Iodine, on the other hand, is a slightly different mechanism, and it's because of the reactivity of iodine. Instead of the iron or the boron or the aluminum, they use some sort of copper salt, so it could be copper nitrate. Much that it's copper, we can actually use any oxidant, and it's in this oxidizing reaction, the redox reaction, that we get the I-. So other examples that are green is oxone, is a green oxidizing agent that is often used, as well as peroxide. Bleach is one, so there are some publications in which people have used bleach and oxone, and so it does essentially the same exact mechanism, and you'll get your iodobenzene. So another example of the halogenation is one in which they do this reaction, or not they do this reaction, but this reaction is done in your body. And so your thyroid actually has an enzyme that does this exact reaction to make thyroxine. And thyroxine is the thyroid hormone that regulates all sorts of biological, biochemical functions. And it basically takes the amino acid tyrosine and adds the iodides. Now notice where the iodides are. We're going to come back to this because where they are is actually very crucial. And so this EMS mechanism happens in your body and specifically puts those iodides there. And it puts it there because of where all the other groups are. And so we'll talk about that. So in the next video, we'll continue on with the other electrophile mechanisms. So in the second video for our class on the 26th, we're going to continue on with ways of making the electrophile. So one is sulfonation, and sulfonation requires concentrated sulfuric acid and heat, which essentially is going to produce sulfur trioxide, and it's that sulfur trioxide in the sulfuric acid that will do the reaction. And so if we look down here, this is basically what it is concentrating sulfuric acid, or it's also called fuming sulfuric acid, and it's in that fuming sulfuric acid that we get this sulfur trioxide that becomes this. So it's an equilibrium. So oftentimes when you open sulfuric acid being concentrated, you will see fumes, and so the way that they actually make this happen even more is just by a little heat. So you need to have heat in the reaction. So if you wrote fuming sulfuric acid, it implies concentrated sulfuric acid and heat. So you've made the electrophile, but this process when we're done is actually reversible. Most of the other mechanisms we'll draw are not reversible. So the other reactions, not really reversible. So this is important because since it's reversible, that means that group can come off. And so we often use it as a blocking group. So if we continue, the sulfur being positive, the aromatic molecule attacks it, and some base in your solution, and oftentimes this is just going to be water. A small amount of water is oftentimes what's used. So it's not sulfuric acid, and it's not the sodium hydrogen sulfate, because that's not, the hydrogen sulfate, because that is not a good base. It's usually traces of water that's in the flask. Now, to remove the sulfonic acid, so for the sulfonation, to reverse it is basically dilute acid with heat. So we'll see this again as a blocking group. So for alkylation, there's a lot more to it we'll talk about, but the generic gist of these reactions is very similar to halogenation. So it's very much like halogenation. You'll take some sorts of alkyl halide. So just an example, you'll have an alkyl halide or some other leaving group like an alkyl tosylate. It's usually halides or tosylates. Please don't try to use other things. And again, your Lewis acid catalyst. So we can use one of these, aluminum chloride, iron chloride, boron chloride. Any one of them for the purposes of this class will work. There is a little bit of differences between them, but for now, this is fine. And it's going to essentially do the same exact thing. One of the lone pairs on the chlorine attacks the MTP orbital of the aluminum. We get this complex, which is highly unstable. And so this molecule will break apart to give us aluminum with the 4 chlorines on there, plus in this case. And so this is going to be very reactive with your benzene. Base will come in, take its electrons from between the bond, and then here we got ethylbenzene. Now, there's a lot more to the story, and we'll talk about alkylation separately. And in the alkylation, there's another thing that we can see is that if you can make the electrophile some other way that we've learned before. So for instance, when we have tert-butyl alcohol, if you add an acid, you can make this become a good leaving group. And by having this a good leaving group, it can leave and you get your tert-butyl cation, which is very stable in this process, but that is still an electrophile that can be reacted with aluminum. So there are other ways of doing this that you've learned before to make the cation, but if you have the primary, this is the only way that we can do it, especially with the primary, is the only way you're going to make the cation. It is not stable, so it will be very reactive.